Good evening. Good evening, everyone. Uh, my name is. I welcome you all to week 7 of tutorials for the ghost properties of materials, nature and properties of materials part 3 with the code NOC25-MM34. Um, I welcome you back again. My name is Sairam Ramachandran. I'm a PhD student from IIT Bombay. And as you all know, the course instructor for this particular course, Properties of Materials, is Professor Ashish Garg from IIT Kanpur. Um, as most of you are well aware of the schedule of how this works or the flow of how this works, we'll start with this week's tutorial sessions where we have 15 questions, and then once we are done with it, we'll have a quick revision of this week's classes. This week we had quite a few very interesting classes. We had covered both mechanical properties, especially the strengthening mechanisms, and then we had discussions on or the introduction to discussions on the electrical properties as well, where we discussed about the basic Drude's theorem, and then we touched upon Sommerfield's model, the limitations of Drude's theorem, and then how Sommerfield had come up with his own model, what are the assumptions on in both these models, and how they contributed towards understanding electrical conductivity and probably even heat capacity of materials better. Okay, without further ado, we'll quickly jump into it. We'll start with the very first question for this week. Uh, right. Okay. Uh, the very first question is the grain size of a metal is increased from 1 micron to 10 micron. Um, the change in the yield stress will be okay. We know that the Hall pitch relation. This is the very first question. The strengthening coefficient K value is given, which is an MPa root meter. We know that there is one property which relates yield stress and the grain size. We know this is called the Hall pitch relation, right? We know this is the Hall pitch relation, and we know the value of Hall. We know the formula for Hall pitch relation to be sigma y equals sigma naught plus K by root D. So from here we get the relation that sigma y is inversely proportional to is proportional, yeah, is inversely proportional to the square root of the grain size or the grain diameter, right? Here we have two cases where D1 has 1 micron and D2 has 10 micron. Our, our grain size has increased from D1 to D2. We know from these relations that the smaller the grain size, better the strength. So they've asked us to compare between the 1 micron grain size and the 10 micron grain size. So we'll do. So they've asked us to change sigma y1 minus sigma y2. So the sigma naught is constant. So it'll be sigma naught plus k by root d1 minus of sigma naught plus k by root d2. Sigma naught gets cancelled. So what we have over here is k times 1 by root d1 minus 1 by root d2. So we know the values of d1 and d2, but these are in micron. So and the k value is in MPa root meter. We'll have to convert these into meters. So it is 1 into 10 power minus 6 meter. This is 10 into 10 power minus 6 meter. We'll go with this. Um, so delta sigma y is k, which is 0.1 given here, into 1 by root 1 into 10 power minus 6 minus 1 by 10 into 10 power minus 6, 0.1 into 10 power minus 6 becomes 10 power minus 3. 10 power minus 3 when it goes up becomes 10 cube. Um, Root 1 into 10 power minus 6 becomes 10 power 1 by root, yeah, minus 1 by root 10 is, just a minute, 1 by root 10 is 0.31 into 10 cube. 1 minus 0.316 into 10 cube, 0.1 into 0.684, right? Yep, yep, into 10 cube. So it will be 0.8.4 MPa, which the nearest value would be 68 MPa. So yeah, we have arrived at the final value to be 68 MPa, around 68 MPa. Do we have an option of 68 MPa? Yes, that is the second option. So yes, the second option, right? Okay, I can see that this color is not very bright on the screen, so I will stick with this color probably. Moving on, the second question. In the grain size strengthening, which of the following is the more probable phenomenon? Grain boundaries act as Frank resource. Dislocation pile up at grain boundaries leading to barriers to dislocation motion. Um Grain boundaries are stronger than the grains and hence the strengthening occurs. Dislocations require higher stress to shear across the grain boundaries. Okay. Again, grain size strengthening refers to the Hall patch relation. Uh, in the discussion, we would have discussed that see, any grain boundary, any grain boundary is basically a barrier between two different orientations of grains. Let's say if but let's say this is somewhat different. We have two different grains like that, and if at all supposedly in such a grain boundary region, we have dislocations which do come along, and then if they come, somehow reach the grain boundary, um, we know that it because of the difference in orientation between these two regions, it is going to be very difficult for these grain boundaries for these dislocations to move from one grain orientation to the other. So there is going it would need additional stress from our side to be able to move from one region to another. So there is going to be a localized pileup of dislocations along the grain boundary because it acts as a barrier to dislocation motion, free motion of dislocation. Uh, we know that happens. The other options are grain boundaries are stronger than the grains and hence the strengthening occurs. Dislocations require higher stress to shear across the grain boundaries. So we know because of the misorientation between the atomic arrangement in in the atomic arrangement between these two or the oriented difference in orientation between these two grains across the grain boundary, there is going to be a pileup of dislocations at this region. because it acts as a barrier to dislocation motion. So this is the most common, most probable phenomenon that occurs, which leads to grain size strengthening, right? And again, so this is what happens. But what actually leads to grain size strengthening is that when we have a case, excuse me a minute, just a minute. This should, this should be better. Yeah. So let's say this is S1, sample 1. And here we have very large grain sizes, which are not, yeah, very large grain sizes. Um, the grain, the cumulative grain boundary area in sample S1, and let's take sample S2, which is heat treated, which we have that we have done multiple heat treatments, or we have made it such a way that you have very tiny grains across the area, right? Just compare these two images, and even from a very basic representation, if we are going to be talking about the cumulative grain boundary area between these two images, these two representative images, we can very clearly see that the grain boundary area in S2, or in my second sample, is going to be is far more than in my sample S1. So these squiggly lines that I've drawn here indicates the grain boundaries. So these are my grain boundaries, right? The grain boundary area over here is definitely much larger than over here. So when dislocations tend to uh, pile up along these grain boundaries, let's say if there is dislocation pile up along all of these grain boundaries, it is definitely going to have a much more profound effect in grain size, in strengthening my alloy over here, or strengthening my material over here, than in the case of S1, where I can count one, two, three, four, five. I can count five different unique grains of different orientations, but here I have a lot more. Okay, so this overall cumulative effects of dislocation pile up across all of my smaller grains and my higher grain boundary area is what is going to effectively increase the strength of um, smaller grain sizes, right? Moving on, the third question, Hall-Petch equation is the relation between grain size and we know this, sigma y equals sigma naught plus k by root d. This is the Hall-Petch equation. We know this is the Hall-Petch equation, where here sigma y is the yield strength and d is the grain size, right? So Hall-Petch equation is the relation between grain size and elastic modulus, fracture strength, yield strength, UTS, it is the yield strength. Okay, moving on to the next question. We have someone joining in. So after every question, I'll read out the question and then I'll give a short pause so that you can try and answer. Um, welcome, Tamilnidhi. In precipitation strengthening, with an increase in the size of the precipitates from cluster level to large sizes, the extent of strengthening decreases all the way, increases all the way, remains constant. First increases followed by a decrease. So I'll just give a short pause. If someone can answer, unmute yourself and answer, we can then have a discussion around it. Okay. So in the lectures, we have seen this particular graph where we talk about the hardness or yeah, we talk about the hardness. Yeah, just give me 1 second, please. Yeah, hardness of this, hardness of yeah, hardness of my material. I'm just representing this hardness with time. So uh, initially there is a short decrease because this is solid solution strengthening. Let's take the example of say aluminum copper alloys or aluminum magnesium alloys, right? And then followed by we have a GP zone, and then we have the theta 2 region. So this is the uh, SSS, solid solution strengthening, and then we have the GP zone, we have theta double prime formation, we have theta prime formation over here, and then finally we have theta as well. So along with these different zones, we can also say that the size of the GP zone is smaller. The size of these individual zones also keep increasing. So theta is larger size in terms of size. Theta is larger than theta prime, is larger than theta double prime, is much larger than my GP zones, right? So in this case, we see that there is an increase in the we see that there's an increase in the hardness to a certain extent, followed by a decrease. So, right? So, so it the hardness or the strength of the material, extent of strengthening increases to a maximum extent, and then it decreases when the precipitate is the largest when it forms the theta precipitates. In the case of aluminum copper alloys, Cu2Al. Yeah. Um, Again, the reasoning behind why this happens is also explained in this class, where we see that when in let's say in a grain, when there are two small precipitates forming, for the dislocation to move, if we have in the plane of dislocation, if we have uh, a precipitate like this, when dislocation is moving, um, when till a certain extent, it is going to shear this precipitate away in such a way that you have the dislocation here, and then so this precipitate is going to be sheared, it's going to be cut across, sheared across, and then for the dislocation to propagate, um, dislocation shearing, precipitate shearing happens to a certain extent. But once the precipitate becomes much larger, once it is quite large, what happens at that point is, um, so once the precipitate size, let's say, once the size of the precipitate exceeds a certain limit, uh, the force required to or the stress required to shear across a precipitate becomes much higher, because the stress is also dependent on the radius of the precipitate, size of the precipitate. Now what happens is that when these two precipitates form uh, are greater than a certain size, and they are um, then the distance between them is also a certain amount, dislocation motion starts have following an Oravan mechanism where the dislocation starts forming loops around along these precipitates. So when we plot uh, when we plot the hardness versus critical size R, so the shearing mechanism is constantly, the strength required for the shearing mechanism is constantly increasing, and the strength required for the Oravan mechanism is constantly decreasing. So there comes a sweet spot, say something of this sort. This R critical, I'll label these. This would be the Oravan on loop. This would be my shear, PPT shear, precipitation shear, right? This R critical would be the ideal size at which I'll get the maximum hardness for my sample. Okay, so coming back to the question, precipitation strengthening with an increase in the size of the precipitates from cluster level to large sizes, the extent of strengthening first increases, as we see here. There is an increase in this region, increase followed by a decrease here, right? So first increases followed by a decrease. That is the answer to this question. Precipitation hardening happens in following alloys. In most aluminum, in most heat treatable aluminum alloys, we can definitely find precipitation hardening happening. So aluminum copper alloys, aluminum magnesium alloys, uh, these two definitely follow precipitation hardening mechanisms. Aluminum alloys. So they can be aluminum copper, aluminum magnesium, uh, aluminum um, silicon, magnesium, manganese. So this is also called copper, also called duralumin, I guess. That's not okay. Even duralumin composition shows. There is a very interesting story behind how scientists figure out that aluminum undergoes precipitation hardening. We will definitely discuss it, and it revolves around this particular composition of duralumin, and German metallurgist called wait, what is his name? Yeah, Alfred Wilm. We will talk about Alfred Wilm's story when we get into the class revision, right? Okay, moving on. The sixth question is, in precipitation hardening, the correct sequence is so. Uh, okay, I will try to fit this diagram in this particular region, but if I'm not able to, I'll probably have to take. Uh, how does precipitation hardening occur in the first place? Uh, right? So precipitation hardening, right? We need to form precipitates. The best way to do that, even during the initial solidification where we take it out to liquid as temperature, and then we quench a system from there. If we are able to optimize the heating rates, cooling rates during the solidification process only, we'll be able to form very fine precipitates or precipitates of appropriate size that gives us the best uh, hardness conditions or strength conditions. If not, we'll have to do uh, solid solution heat treatment processes where, let's say we have, let's take the example of the aluminum copper alloys or some random alloy system AB. Drawing the phase diagram of AB. Okay, we have A, we have B, percentage solute. Going towards it, let's just say this L, alpha, beta, alpha plus beta, L plus alpha, L plus beta. Okay, this is a binary phase diagram, a very simple representation, a very crude representation of it. Let's say we have the AB system, we have the 100% A metal here, 100% B over here, percentage solid solubility as the line goes. And as you can see from here, this is the invariant reaction line, which is given by this. So this is the invariant reaction line, and this is the eutectic reaction point. So if you have undergone any phase transformation courses or uh, basics of metallurgical thermodynamics, these invariant reactions, eutectic points are something that you should be very familiar with by now. Okay, coming back to the question over here, what we have here is, let's say we have our composition somewhere over here, x percentage b, a x percentage b. X percentage b is what we have. That is the alloy system that we have been given. Now we have a solid block of x percentage b and 100 minus x percent of 1 minus x percent of a. Okay, that's what we have. Now we heat treat this alloy all the way to temperature T1, and I'm going to be showing these things in this graph over here. And simultaneously I will draw temperature versus time plot as well. So this is what we call a TTT diagram of sorts, uh, and this is a basic representation of a phase diagram. This basically tells us what is going to be our heat treatment cycle, right? This, the diagram below, is going to tell us our heat treatment cycle, and this is going to tell us what are what are the temperatures at which we are going to be selecting our composition at, right? Um, yeah, we'll do the heat treatment at temperature T1. Why are we doing that? See, anywhere in the single phase region where it is represented by this alpha, uh, in this region, if we treat a sample to anywhere in this region, it is going to homogenize in the single phase region into a complete alpha with a full alpha region. Only when it crosses this sol west line over here, solid west line over here, are we going to have precipitates of beta forming in various locations in our alpha matrix, right? And then the second step would be to optimizing the temperature at which we cool it down to, or hold it so as to form the right size of beta precipitates. Okay, so initially we heat it up to T1, and then we solutionize it in this single phase region over here, in this alpha phase region over here. Now what we do is, from this T1 I quench it immediately, so that I get, so when I heat it to T1, so first step is heat to T1, I get alpha phase. 2 is quench to room temperature. What happens right now is I get alpha because I am not giving the beta atoms to atoms of solute B to segregate, to diffuse across grains or grain boundaries across the uh, lattice so as to be able to form the beta phase. And now what I end up is with a supersaturated alpha at temperature, at room temperature. The next thing what I do is I heat my supersaturated alpha again to a temperature somewhere in this two-phase regime, somewhere in this alpha plus beta regime, but at a temperature lower than my invariant reaction. Because if I heat it to this temperature, um, in this two-phase regime, I am going to trigger the eutectic part, which is definitely going to, which the eutectic composition will have the lowest possible melting composition. I don't want to achieve, I don't want to do, I don't want to go anywhere near that. So what I do is, let's say I heat it back at, this is the temperature that I heat it back to. Let's name is T2. T2. I'll hold for some time for my precipitates to grow to the right size, because as we discussed over here, it is a time dependent growth um, of my precipitate. So it depends on time and the temperature. Um, so heat hold for precipitate growth to appropriate size, because as we see, there is an R critical which is going to give me the highest hardness. Below this, it is still developing. Above this, there is going to be a decrease. And I know there's going to be decrease because even though the strength required to shear through uh, a larger precipitate is higher, we know for a matter of fact, a lot of these things take the path of least resistance. So if the Oravan loop mechanism is going to give it an easier path for dislocation motion, the path of least resistance is the Oravan loop mechanism, and that is what is going to follow. Okay, now hold, and then if I know at a certain point I have achieved from say various kinetic models, I am able to determine that at after holding for a certain temperature, I am able to achieve the hardest material or the right size. I cool it down or quench it depending on what I want. Right. So how does this heat treatment look? So what I am doing is, from room temperature, I am heating to temperature T1. I solutionize it, hold, so that I give time for the entire material to become completely alpha, and then I quench it immediately within a very short span of time. I quench it, bring it down to room temperature, and then now I find an appropriate temperature T2 and hold it for a long time. Right, I hold it again, and then now I have, depending on how I want my strength to behave or my power material to behave, I can either slow cool it or I can quench it again. Right, I have two different: cool and then quench. This is a quench. Right, this is what I have for my material. Okay, so this is the heat treatment cycle. So this part, say from point A, B, C, D, E, F. Okay, my part A to D is called the solutionizing treatment, or rather, it's actually A to C. A to C is the solutionizing. It's the solutionizing treatment. Okay, and then I heat it to a temperature, um, followed by quenching. So one thing that I have to note down is in the solutionizing treatment, it is always done in the single phase regime, in the single phase region. So heating followed by heating this single phase region. So this option is definitely not going to work because this is in the two phase region. Everything else in the single phase region, good. And after that, I don't slow cool. So my option B is also cut. So I have basically to choose. I have to choose between option C and option D, which is heating, solutionizing in single phase region, quenching. What is going to be my next step? What is this T2? This T2 is at a temperature below my invariant reaction. So that's what we saw here. It is at a temperature below this invariant reaction. It can be, see, this T2 can be even as high as over here because the formation of precipitates and the time required to form precipitates depends on the temperature because it's diffusion dependent, right? Diffusion, as you all know, follows the Arrhenius laws, which is time and temperature dependent. Uh, so yeah, it is going to be below the invariant reaction. So and then it has holding followed by cooling. So the correct sequence for precipitation hardening is option D. Okay, moving on. For an impurity atom to cause solid solution strengthening, uh, it can be substitutional atom but bigger than the host atom. It can be substitutional atom but smaller than the host atom. It must be of the same size as host atoms. It can be small and interstitial atom. Okay, back to over here. Let's say we have a series of atoms material over here. Now, as we all know, in solid solutions, when we basically when we add an impurity atom or a dopant or an alloying mixture, it can be of two types. One is substitutional, and the other is interstitial. Right? We have two different options of alloying, two different kinds of alloying. The next is, so what is substitutional? Substitutional is, so if this is my host atom, if this is my host atoms, then what I do is that if what is substitution? So uh, I have I have a series of pens of the same kind here. What I do right now is I'm substituting this pen for something else, right? So this is called as a substitution, just like in any other game. If the impact substitution that we have in our IPL these days, or the substitutions that have been done in football and many other sports for ages right now, right? So what they do, they replace one player with a different player for their own benefit, right? So that is what is substitutional. And the other type is, so we see these gaps over here, right? Our atoms can be placed in these small gaps over here as well. So this blue dot that we have kept in between is a representation of the interstitial alloying element. Okay. Now the host, the substitutional atom will sit somewhere over here. So for it to have a strengthening effect, this substitutional atom can either be bigger, in which case it is going to displace the atoms to its sides, thereby having a compressive effect on the atoms in the surroundings, or it can be smaller as well. If it is smaller, what would happen if my substitutional atom is smaller? Then these atoms have to are pulled or attracted towards it, creating a tensile region. Okay, so depending on whether the atom is bigger or smaller, it could have both a tensile or compressive effect. The same is the case with the interstitial as well. So if the interstitial atom is much smaller, there is going to be a draw towards these. But if the interstitial atom is much larger, that is also going to displace my atoms from their mean position. So which might have a compressive strength again, compressive effect again. Right. Anyway, irrespective of whatever happens, whenever there is displacement of my atoms from their mean position, there is a localized strain that is formed in the vicinity of the alloying element or the impurity atom, and these these local strains act as a barrier to free motion of dislocation. So I'll have to add a lot more energy. I will have to stress my material a lot more for it to be able to move these strained regions, localized strained regions, for it to move from one end to the other, right? So this is what this is the fundamental mechanism of how solid solution strengthening works. Okay, so my substitutional atom can be bigger, can be smaller, and it can be a small interstitial atom as well. It can be any of these things. What why why can why can't my atom be of the same size as of the host atoms? If that is the case, it is going to seamlessly replace my host atoms, and it is not going to create any lattice distortion. It is not going to have any strain effects in my lattice. So in such a case, how is it going to affect my uh, or improve my material at all? How is it going to provide strengthening to my material at all? So that is not the right answer. Okay, moving on. Week 7. Which of the following is or are not strengthening mechanisms in pure metal? Okay, the main point over here is this is a pure metal, right? Grain size reduction can be done in pure metals, so it is purely a matter of having the right kind of cooling rates or heat treatment mechanisms for me to play with the grain size reductions. Hall pitch relation has nothing to do with if it's an AA bond, it's an AB bond, BB bond. It has nothing to no correlation with that. But say same thing with stain hardening as well. It is purely a material dependent property. Once you stain your material, once you take it beyond the plastic limit, so let's say I take my material beyond the elastic limit once, and then I come back to zero phase regime. But now if I want to plastically deform my material, so let's say this was sigma y1 initially. Now because I've already plastically deform my material to the stress sigma 2, for me to plastically deform my material after bringing it back down to zero stress or zero stress condition, I will have to strain it for me, for this material to yield right now, I have to strain it beyond the sigma 2. I have to apply a stress beyond sigma 2, right? So this is, so we can see that there is an increase in the strength, yield strength from sigma y1 to sigma 2. This increase is because of strain hardening. Again, this is still possible with a pure metal, so no problem at all. However, when we go for a solid solution strengthening, this is very clear that you need a solute atom. Right, as we had discussed above, only in the case of a solute atom, it can be substitutional, it can be interstitial, it can be of bigger size, smaller interstitial atom, it can be any possible configuration. This localized strain is what is going to give us a strengthening mechanism for solid solution strengthening. So we need a solute atom. So it cannot be done in a pure metal. Okay. Next is precipitation hardening. Very similar. This solute atom might have a solubility limit in my material. So again, even for precipitation to form, I still need a solute or alloying. Right? I still need these to um, bring in or increase the strength of my metal or my material. Okay, so which are not the strengthening mechanisms in pure metal. Solid solution strengthening and precipitation hardening are not strengthening mechanisms in the case of pure metal. In the case of pure metal, I can still do grain size reduction, I can still do precipitation hardening, I can still follow hollow pitch hall pitch relation for increasing the strength in the case of pure metals, but and even in stain hardening, but I will not be able to perform solute precipitation hardening. So that's why, again, very fascinating story about Alfred Wilm and how he got aluminum alloys. Right, very interesting story, very fascinating story. We'll definitely discuss about it. Okay, I think with this eighth question, we have officially completed the mechanical properties of materials. We move on to the electrical properties of materials from the ninth question onwards. Uh, what is the approximate range of sigma or the electrical conductivity for the semiconductor is we know that sigma for metals is greater than 10 power 6 ohm meter inverse. Sigma for insulators is less than 10 power minus 6 ohm meter inverse. So if there is anything in between, so we know that sigma of metal is greater than sigma of semiconductor is greater than sigma of insulator. So what we end up with for semiconductor is 10 power 5 is greater than 6 is greater than something is greater than 10 power minus 6. So anything between the range of 10 power minus 6 to 10 power 5 or 10 power 6 ohm meter inverse is going to be the value of semiconductor, right? Okay, so is there the option for this? Yes, the very first option. This is the range of electrical conductivity for my semiconductors. Okay, the next question for this tutorial is electrical conductivity of a metal can be expressed as R is in R is resistance, is cross-sectional area, length, electrical field, voltage. So we know that resistance R equals rho L by A, right? we can confirm it quickly from the class notes as well. Yes, R equals rho L by A, and so which means rho equals R A by L, and rho is the resistivity of a material. Resistivity of a material. And we know the conductivity equals 1 by rho, right? So conductivity equals 1 by RA by L, which is L by R into A, which is sigma by conductivity, right? Okay, so conductivity is L by RA. We have that value over here. Moving on, uh, we have a few participants right now. According to the classical theory of electrical electronic conduction, the Drude and Lorentz model, resistivity of a material rho is directly proportional to. This was discussed in the um, I think the fourth class of this week, the introductory class to electrical conductivity. Um, the options are proportional to t power half, proportional to t, proportional to t power 3 by 2, proportional to t square. I'll wait for a few seconds. I'll pause for a few seconds. Someone can unmute yourselves and try to explain this. You can answer this question. Okay. Um, so while discussing about the Drude's model of electrical conductivity, this was one of the problems that actually led to people thinking, is the Drude model the right model to understand electrical conductivity in materials, in metals, right? Because as per the Drude's model, the resistivity of material was proportional to T per half. And again, why is this coming? This is coming from the they knew that half mev square is the kinetic energy, but this also equals to 3 by 2 kbt. Uh, so from here, they knew that the velocity is proportional to t power half, and we saw that we can derive an expression connecting the velocity and the resistivity of materials. So which means the resistivity is also proportional to t power half, right? Um, okay. However, experimentally, this is from the Drude's model. However, experimentally, they found that resistivity is directly proportional to the temperature power 1. So the professor in professor's class would have even drawn this diagram where so, right. Yeah, my straight line is not a very good straight line. Apologize for that. this has this is some b t power half, and this is some q a into t resistivity, right? Okay, so the answer is proportional to t power half. Yeah, so we this was one of the inconsistencies of the Druth's model, which made us question about uh, the value. Um, if you could just give me 1 minute, I have multiple. It's okay. The next question is the minimum number of energy states required for complete filling of the electron in the energy levels is again because we have to follow the Pauli's exclusion principle. But if we have, which basically tells us that at every energy state every energy state should be filled first before we go on to the next state. So for every positive spin, there has to be a negative spin, and if we have total of n number of electrons, then because at each and every energy state, 2 electrons are being used for every energy state. So we'll need a total of n by 2 energy states to fill all n electrons, right? So the answer is n by 2. Next question. At absolute 0 Kelvin, the maximum energy level that can be filled is the options are conduction band edge, vacuum level, valence band edge, and the Fermi energy. So the value for this is actually so at absolute 0, um, once we have multiple energy levels and there is an increase in energy, when we have n electrons, uh, uh, if we fill all these electrons across these energy states, the highest level that it fills, it's called the Fermi energy level. At T equals absolute 0, every state below the Fermi energy level is completely filled, and every state above the Fermi energy level is not filled at all. So, Fermi energy level is the answer. The resistivity of a metal can increase with an increase in impurity concentration, percentage deformation, strength, and temperature. I'll pause for a second for you to give a thought about it. If someone can unmute and answer, please do. This is a very interesting question. We can You can give it a try. The resistivity of a metal. We are talking about the resistivity of a metal. Rho R equals rho L by A, right? Yeah, R equals rho L by A. So we are talking about this rho over here, which is we know that this is an intrinsic property, and we also know from an earlier question where we discussed that yes, from this 11th question we know that rho is rho is directly proportional to T, so temperature is definitely a thing. But rho can also be disturbed by the impurity concentration and percentage deformation. So when a metal is deformed, it will also affect our intrinsic resistivity, our resistivity of a material, right? Okay. The last 15th question for the in a metal, the electron concentration is 10 power 24 per meter cube. So they're basically giving us n. The density is 10 power 24 per meter cube. Okay. Electron relaxation time tau is 10 power minus 10. We are given Me. We are given Q. What will be the electrical conductivity? So from the formula we know conductivity sigma equals N E square tau by ME. So we just have to substitute everything right now over here. 10 power 24 uh, into E square, which is 1.6 into 10 power minus 19 coulomb into it will be coulomb square. Okay, square this, and then we'll have the relaxation time, which is 10 power minus 10 seconds divided by the ME, which is 9.1 into 10 power minus 31 kg. Okay, again, all these things are already given in their um, right units. Very simple equation, right? From just by looking at the question, even without having to solve any of these things, if we want a very simpler way, we can say that we know the units for electrical conductivity, which is ohm per meter inverse. So wherever there is no inverse sign, ohm meter and ohm centimeter, we can automatically reject these two values straight away. The next thing is ohm centimeter inverse and ohm meter inverse. When every other value is given in apart from kg, if we convert this to grams, everything else is given in their SI units already. So we might have to we have already eliminated two of these options, so it's going to be either 2.8 into 10 power 6. The 2.8 into 10 power 6 is going to remain the same again. It's either ohm centimeter inverse or ohm meter inverse. That's the only thing that we have to worry about. Again, if we solve all these things, again kg into 10 cube, add everything. When we solve for everything, we end up with 2.8 into 10 power 6 ohm meter inverse. Okay, so option C. Okay, let me just take a short break, and then we will have for me to drink water. Someone has been calling me multiple times. I'll check what that is also about, and then we can resume our session. Uh, let's meet back in a few minutes, right? Okay, thank you. Okay, um, yeah, we are back. Before going on to revise uh, other topics or previous week's assignments or tutorials, what I will do is that we will quickly go through this week's lecture because I was really fascinated. I was really interested in this week's lecture. It was very beautiful. I really enjoyed multiple aspects of it. Um, right out of the boat, we have we discussed about two broader areas, right? So, yeah, week 7 tutorial. I really enjoyed listening to this week's classes because we completed last week. We were discussing about the various slip systems. um, how do these how do the slip system movement, say, how does screw movement or edge movement or mixed dislocation, how do any of these help in strengthening my material, how much what is the stress related to for these movements. I think we had seen some demonstrative figures from um, during the class with very beautiful visuals on various of these things. And finally, we all of this we concluded all of this to say, how does all these things help in strain hardening or strengthening STR, strengthening mechanisms, right? So we saw that there are four, may we can see we can classify our strengthening mechanisms into four major categories. The first thing is the first thing is strain hardening, which we saw last time. First topic was strain hardening. We saw the details of strain hardening last week only. Uh, the second one was grain boundary strengthening. Third one was solid solution strengthening. And then the fourth one would be the precipitation hardening. All right. We saw these are the four major strengthening mechanisms for any given alloy, and uh, so what's happening here is that once we are done with all these strengthening mechanisms, we were done with the mechanical property aspects of materials, and then we also stepped into the world of we had an in basic overview or introduction to the electrical conductivity of materials, right? We saw Roth's theorem, we saw the limitations of it, we saw how Sommerfeld's model overcomes these limitations, overcomes some limitations from Droid's model, right? And then we saw the I want to say a jack in the box, uh, but yeah, it's basically electron in a box model, and how we can use uh, the electron in a box model with uh, wave nature of electrons to determine what happens and to have a basic version of have the fundamental form of Ohm's law, right? We saw all these things in this week's class, and we will get started with the strengthening mechanisms. What happened in the strain hardening, uh, which we have seen in the past: grain boundary strengthening, solid solution strengthening, precipitation hardening. How did it go about? Right? Okay. Now we will go back to this week's notes. Okay, yeah. So the recap from week 6 was that the strain hardening or the work hardening effect in materials. Uh, as I had mentioned, so when we work harden our material beyond its yield point over here, when I plastically deform a material, let's say I move to this sigma 2 regime, I come back down to zero stress region, and then when I have to deform my material again, when I keep increasing, I would not be able to plastically deform a material unless and until I cross this sigma 2 threshold, which I had already crossed. So there seems to be an increase in the yield strength of my material from sigma y1 to sigma 2 because I have already plastically deformed my material till sigma 2. I'll have to deform it more than sigma 2 for me to able for me to be able to see any visual changes, or for me to be able to visualize any plastic deformation, any further plastic deformation to my material. However, we have to note, we have to be very careful that the Young's modulus remains constant even irrespective of the plastic deformation that is happening over here, right? But along with the strain hardening or the work hardening, the ductility of my material also decreases. How does this happen? How is the strain yield strength increasing? Yield strength seems to be increasing because of dislocation interactions, and yeah, that we have seen a whole lot of it, where the Frank Reed sources start to operate, multiple dislocations are created because of Frank Reed sources. We form all those loops, and then interactions between various dislocations. We have also seen that there is a when you have the Frank Reed sources growing, there comes a point where there is annihilation between opposite directions of sources, uh, and then there is a formation of sessile dislocations as well, dislocation pileup. Uh, we have a lot of these things, and finally there is an increase in stress required to cause further deformation or further plastic deformation. So this is the basics of what we see in uh, yeah, strain hardening. Just give me a minute. Very sorry, there is some outside noise coming from outside my room. But yeah, let's continue with the class. The second strengthening mechanism that we saw is the grain boundary strengthening mechanism. So, and when we talk about the grain boundary, we have two basic types of the grain boundary, which we can say as low angle grain boundary, which we can define as the low angle grain boundary, and the low angle GB grain boundary, and the high angle grain boundary, the large angle grain boundary, right? Our major focus would be with the large angle grain boundary, because the process of grain boundary strengthening in the low angle grain boundary is quite a little bit different and not in the scope of this course, this lecture right now. Um, and again, we are more concerned about the polycrystalline material. If we are able to have a polycrystalline material, why is that the case? Um, we know in a polycrystalline material, all various grains are oriented along different directions. So, which means even if it is the same atom, uh, there is going to be the orientation of those atoms are going to be slightly different. For in my strain hardening, we saw that because of Frank Reed sources, or because of the interaction between dislocations, uh, say formation of sessile or formation of dislocation pileups, or for any other reason, I have if there is no easy or convenient path for my dislocation motion, it is going to create I would have to generate, I would have to uh, apply more stress for my dislocation motion across for my dislocation to move, right? In the case of grain boundaries as well, because of misorientation or because of uh, mismatch in the, I will not say misorientation, because of mismatch in orientation across the two grains, across the grain boundaries, it is going to act as a barrier for the smooth motion of my dislocations. So when we have all these large angle grain boundaries, there is going to be a pileup of dislocations. So what I have over here, uh, at the grain boundary, there is a discontinuity, and the slip plane is not extended because there is a mismatch of orientation between across the grain boundary in these two grains. So dislocation cannot move easily across the grain boundary to the next slip plane in the to the most favorable slip plane in the subsequent grain. So what happened here? I need to provide more stresses for the deformation to occur. So when I'm not able to do that, uh, the grain boundary acts as a barrier to dislocation motion. So, and along the grain boundary, there is a pileup of dislocations in the slip plane. Okay. Now, this pileup would need higher amounts of stress for deformation, and this is one of the most important methods by which grain boundaries strengthening occurs. Now, smaller the grain size, more is the area of grain boundaries, therefore more are the barriers and I would need higher stresses. So there is a relation called as the Hall patch relation right now, where it is given by sigma y equals sigma naught plus k by root d, where k is the strengthening constant. We have already solved a problem in this initially, okay, by root d. So sigma y is proportional to 1 by root d. When the d is larger, sigma y becomes, sigma y decreases, correspondingly sigma y decreases. When my grain boundary size reduces, my grain size reduces, sigma y increases. Okay, right? Yep, we see this. Yes, this is the relation, right? Very very important. All patch relations. One more very important thing is that this grain boundary strengthening is a mechanism of strengthening even in the case of pure alloys. You don't need to have an alloying element or an alloy or any of you don't need to have an alloy system for this strengthening mechanism to work, right? Yes. Now this is the how to achieve how to achieve. So we know that we need small grains sizes. Okay, what are the methods to achieve these small grain sizes? One is basically something like a top-down approach, where right when we form the basic microstructure of this crystal only, we can try and make sure that we are able to form these very large this we are able to form these very extremely fine structured microstructures, and to be able to do form these very fine microstructures, we have to have a very good handle on um, the thermodynamics and the kinetics of a system, because during solidification, so when we have a molten metal and when we want to form a very fine microstructure, we have two mechanisms which are actually competing in nature, which is also dependent on time and the temperature. Okay, so these two mechanisms are, one is nucleation and the other is growth. Both of these things are a function of temperature and time, right? Very, very important. Why? When I I have a bath of molten metal, I am cooling this molten metal below its liquidus line, uh, so that I can form a solid. Now, these, because it has so much energy, heat energy with it, just because I cool down my temperature right below the cooling solidification line does not mean that my sample will solidify easily. What I have to do is give something called as a degree of undercooling, or I'll have to cool my molten metal to a temperature delta T below my solidification line, so that solidification starts occurring. Now, in this huge vat of molten metal, what starts happening initially is called the nucleation stage. So the first step is the nucleation step. So this is the nucleation step. So again, remember, I am continuously cooling my material. I am not cooling, so I am not cooling my material to temperature T1, holding it, cooling it, holding it, cooling it, holding it, cooling it. No, no. From the molten metal, let's say I'm melting some aluminum alloy or some other alloy. Taking it to a temperature of 1600 degrees. To a, if I go to 1600 degrees, even steel is iron is going to melt. So let's say I have 1000 degrees. From 1000, I'm going to be continuously cooling it to the room temperature or probably below that. But I'm going to do this. My microstructure is going to depend on my cooling rate rather than the temperature at which is cooling. So right now, if my cooling rate is very, very fast, I am going to form very small nuclei. That is the very first step. I have my nuclei formed. Now, as soon as my nuclei will form only, and it will survive only if the critical radius of this nuclei, there's something called as the critical radius of the nuclei. So the terms used during nucleation is very similar to the terms used for I'm very sorry. For anything, I'll say there is an embryo that is formed, and then the embryo grows slightly. Only when the radius of this embryo exceeds or is equal to the critical radius of the nuclei, only then we say that there is a stable nuclei that is formed. Now, as soon as the nucleus forms, there are two reactions right now. The molten metal has two reactions happening parallelly. One is further nucleation at lower and lower temperatures, and the second one is the growth of the already formed nuclei. So over here we have we, we not only have these nuclei, existing nuclei growing, but we also have other smaller nuclei forming, right? And it is always a balance. So the entire process of nucleation growth is a balance between time and temperature. So this formation of these secondary nuclei is also very important, because these can also help us in reducing or limiting the grain size, limiting grain growth, and a lot of other factors, right? So what happens right now is uh, we will have to maintain the cooling rate in such a way that after a certain point, uh, to the maximum extent possible, we prioritize nucleation and try and reduce grain growth. In order to do that, we have to cool down very, 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 very quickly. So we should not, only when we allow time at any given temperature, or the cooling rate is relatively slower, will we are we allowing time for the growth of the small nuclei or the nuclei that formed initially, right? When we don't allow time for the initial nuclei form to grow at all, we can achieve very fine microstructures by fast cooling rates. Limit grain growth or nuclei growth, right? Slower cooling means higher lower nucleation rate and higher growth rate, which forms coarse grains. And very fast cooling will be able to have higher nucleation rate and lower growth rate, giving leading to smaller and finer grains. Okay. The other method by which I can do something is called a cold deformation followed by thermal treatment. And this cold deformation can be anything from rolling to forging to extraction, extrusion. Can be anything followed by again. Why do I need a thermal heat treatment after this? When after my cold deformation, my sample is going to be extremely tough. It's going to be extremely hard. It's not going to be. It's going to be. It might even be extremely brittle. And for me to alleviate these negative impacts on my strengthening mechanisms, I will have to do a post-processing heat treatment for me to have a very good material. So again, in this case, I've already cooled my metal from liquid from its liquid state. I already have a solid metal. I have some microstructure, let's say undeformed metal, which has a large microstructure, which I'm not very pleased with. So what I do in this case, for me to have such oriented crystals, oriented grains, I might have done some process like rolling or extrusion for me to have such elongated grains. And now I basically heat treat it, which means that I'm taking my grains to a solutionizing temperature, and then from the solutionizing temperature, depending on the temperature at which I am cooling. So if the delta T, which means let's say the heat treatment temperature is T1 and this is T2, the delta T that I provide, which is my T1 minus T2, if this is high, then I get a recrystallized grain with very small grain size. But if my delta T is low, then I end up with a coarse grain structure. Okay, this degree of undercooling that I provide is also very important. This undercooling is a very common word when we talk about heat treatments in metals and materials. Uh, it is the same term for undercooling when I have to apply it for molten metal to solidify, for these materials to recrystallize and then grow again, for anything. Okay, at the end of the day, to conclude everything, for me to be able to grain boundary strengthen my material, I need to have more grain boundary area, which means I need to have very fine grain structures, very fine microstructures, very small grain sizes, and I can achieve it by two methods. One, controlling the rate of cooling from my liquid metal to my initial microstructure, or by a post-processing heat treatment and deformation mechanism. So next method is by solid solution strengthening. Again, so we have discussed this to a certain extent during the class hours, so during the tutorial session, where, as described over here, a solid solution, solution meaning a solid solution means I have to have more than one. So I have my solute or my base or my matrix, and then I have which is the host atom, and then I'm adding something onto it, which is my solute atom. So my solvent is my base, which is the host, and then I'm adding my solute or the impurity or the additional alloying element. And this could be of two types. One is the interstitial, which means these green ones are the interstitial, and then the red ones here are the substitutional atoms. These could be of these two types. Now, how is it that these are going to uh, have an effect in this strengthening? My impurity atom, my solute, should be either bigger or smaller than my host, preferably, especially if this is substitutional, right? If my impurity is interstitial, even if my interstitial sites, the sites that we see here, because as these are rough sketches, we are able to see that the interstitial sites are also approximately of the same size as my atom, but my interstitial sites are not going to be of the same size as my atom, or probably larger. It is so if my interstitial site has a very similar uh, atom of a very similar size to that of my host material, even then it is going to strain the local lattice, because of which I am going to observe some straining, some compressive stresses, some there is going to be distortion in my local lattice because of the substitutional or my interstitial impurity or solute atoms. And when a dislocation tries to move through these distorted or lattice strained systems, I would have to, yeah, it could be either tensile and compressive, depending on the nature of material. So let's say in a ceramic material, I would prefer if I have a compressive stress in my local lattice. If it is metallic, tensile stress would work well, no problem at all. Um, Depending on the kind of material, depending on the kind of application that I want, I might have to play with either a tensile stress, tensile localized stress, or a compressive localized stress. Having said all this, what happens when these point defects start interacting with my edge dislocations or my line dislocations? So now there are two things that are going to happen when my substitution atoms or my solute atoms are going to come and interact with my the dislocations. One is that my lattice is already strained, and if I want to move my dislocation across the strained, if it is not in the exact same line as my dislocation, then I'll already have to need there's already a need for me to provide a higher stresses for my dislocation to move across this distorted plane. The next thing is, if I have a line dislocation and if I have something like an interstitial atom or a substitution atom which is creating a deformation, then when this line deformation passes through and it comes in contact with this, so this is basically going to form, this is going to be settled along my edge dislocation, and this is going to form a very stable dislocation, right? So when I in the case where it was initially strained because of the solute atoms, now my dislocations have interacted with my strained atom, strained solute, and then it has somehow formed a very stable dislocation. So for me to be able to move this very stable dislocation is going to cost me a lot more stress, right? So adding an impurity atom, there is going to be a localized change in the bonding nature as well, and this could very well change this could change my elastic modulus as well. So which means there is again an increase in my yield stress as well. Okay, as mentioned here, all these things depend on the concentration. Some in some cases, even with a very small solute concentration, I will be able to achieve much higher stresses. But in the case of other systems, I might have to add a lot more to be able to achieve for me able to achieve a lot more. I have to add a lot more concentration to be able to achieve any significant change in mechanical properties. So the very common example is with zinc here in copper, zinc, and brass, because the size of copper and zinc over here is very, 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 very similar. uh, for me to be able to achieve 100 MPa increase in my yield strength, I will have to for my yield strength to be able to reach 100 MPa for my copper, zinc or copper nickel alloys, I'll have to add a lot of alloying elements. So almost 20 to 30% of solute atoms would need to be added for me to be able to increase my yield strength. However, in the case of say copper tin or copper beryllium or even in the case of copper silicon, uh, substitutions lesser than 5%, lesser than 10% is sufficient to be able to increase my yield strength from say 50 MPa all the way to 200 MPa. And this is purely from what we have discussed above, right? So we have a lot of these solid solution strengthening examples. The very common example is iron, which is a iron carbon uh, example, copper zinc, which is brass, copper tin, which is bronze. Uh, I've always been confused with what is brass and what is bronze. The very simple thing that I found which is actually very useful for me is brass has S, but S does not have Z. So in the copper zinc Zn, the alloy forms the name of the alloy does not have a Z. It has only S. So copper zinc forms brass, not brass. Similarly, copper tin, which is Sn, CuSn, has the name has the character Z in it. So copper zinc forms bronze. This is a mnemonic device that I have devised for myself to remember what is brass and what is bronze. Okay, moving on, we have the next thing, which is we have seen what is strain hardening, we have seen what is grain refining or grain boundary hardening. We have also come across the solid solution hardening. The final thing that we have to look up is precipitation hardening, precipitation strengthening, or precipitation hardening mechanism. So again, we have to add solute atoms, and we need to add as much solute atoms so that there is something precipitate out. So we have to move beyond the solid solution regime where we don't have a secondary phase, we don't have form a secondary phase at all, but it is the same. But for the precipitation hardening to take place, we are interested in the formation of a second phase, right? To be able to what happens when impurity added is beyond solid solubility limit, formation of second phase harder, stronger, it can cause precipitation strengthening, right? So this is what the precipitation strengthening is all about. Um, Again, very common examples are steel systems where alpha iron is very soft, but Fe3C, the cementite phase, is very, very hard. So this hard cementite phase is with different microstructures is what rules the world right now, with so many materials, so many applications having steels, different shapes, different kinds of steels with so many varying properties, material properties. Um, So the next is aluminum copper alloy systems, formation of precipitates. Again, Al2Cu precipitates are formed, which are harder than the typical aluminum systems. Um, yeah, rather than over here, I would take you back to the materials where we discussed about this in detail. Where, yes, right, we had given a very simple example of this. Now we have a binary eutectic phase diagram over here. A B system, A moving towards B. Uh, what is the sort of so what is happening here for me to be able to form the precipitates, and the precipitates should be of the right size. Right. Even before I go any further into any of these topics, I really want to uh, discuss about how did they start understanding about the precipitation hardenability in aluminum alloys, right? Um, so way way back in the day, researchers, so they knew very well, they knew a few facts very well. So okay, I'll go back to my notes. So this is history of precipitation hardening of aluminum alloys, right? So uh, scientists found out that iron became stronger when they added when they added a particular range of carbon to it, so which is the steel as we know. So steel is much stronger than simple iron. Okay, now they knew one more thing: density of aluminum is much less than the density of iron. If I'm able to achieve very good very good strengthened aluminum alloys, then I can replace aluminum alloys in a lot of places where weight and density are a major considerations. Let's say automobile body parts, aircraft fuselages, and probably a lot of other applications where I'll be able to reduce the overall weight of the system. I'll be able to use aluminum alloys, which are far more easier to machine, to shape, etc. And then aluminum alloys, I know for a matter of fact that they have quite a bit of corrosion resistance as well, because they form a passive layer of alumina on top of it, and then they have good corrosion resistance as well. Um, it has so many advantages, but the major problem was aluminum was soft, right? So they derived lessons from steel and so many other characteristics. They said that, can I add some solute to aluminum to make it stronger? So during this discussion, we have a very important scientist, German metallurgist, who comes in and who says that his name is Alfred Wilm, and he dedicates uh, his time and research towards aluminum strengthened alloys. Okay, so what he does is let me just check if I have the exact composition of this. Okay, maybe not. So what he does is he adds aluminum, copper, magnesium, manganese, and probably silicon as well. And then this is called the duralumin. He adds all these things. He melts it, uh, uh, and then he casts it, heat treat, casts it, quench, heat treat it, again quench it. He does everything, and then is he able to form a hardened alloy, much more strengthened aluminum alloy? Whatever he gets through this, let's say this is the first trial, he still has a soft aluminum alloy. He keeps reiterating with, he reiterates, or he plays with the composition, with the aluminum alloy composition, heat treatment cycles, He plays with a lot of these things, and he's still not able to get aluminum alloys. One day over the weekend, what he does is he's performing an experiment, uh, and then uh, he he creates a large batch of aluminum alloys. He takes a few out, he quenches it. So what what he does over here is, sometime over the week he has done so. In his nth iteration, he has created a large batch, multiple rods or multiple cast products. He has quenched it, he has put it to heat treatment. He has taken a few of those out, and uh, he has quenched it again. And then he still feels that he's able to see that he has still not been able to form strengthened aluminum alloys. Out of frustration, he leaves the lab immediately, forgetting that he still has a few cast products in the furnace. Okay, he goes out for the weekend, he takes a vacation, he comes back to the lab after a few days. Let's say he takes a vacation of a few hundred hours, 3 4 weekends, 3 4 days. He does not come back, he does not, he forgets that there is aluminum alloy billets, cast products still in the furnace. Right? He completely forgets about it. He's just oblivious to it. What he does is that he goes on a boating and fishing trip. He takes a considerable amount of vacation time. He does this. He enjoys his time. He comes back, notices he has left the furnace on, and some alloys, alloy billets are still in the furnace, right? Now what he does is that, anyway, he thinks that it is completely waste of time to even bother with them. So if he takes it, he quenches it, and uh, he throws it away. But now a few days go by, and then now he thinks, in his mind he determines this experiment to be a waste of time. But now he takes this material which has been in the furnace for a considerable amount of time. He tries to deform it. He's not able to deform it. He finds it to have somehow strengthened. Now what he does is that he understands that the heat treatment process for an aluminum alloy is not the same as the heat treatment process for a steel system or steel alloy. So he understands with time he has been able to strengthen the alloy, and then he go back to, he cuts the sample, he go back to, he sees the sample microstructure under SEM, under TEM, under microscopy. He is able to see fine precipitates being formed in the aluminum alloy composite matrix, in the aluminum alloy matrix. He determines what is the composition of those alloys, and then he does a time temperature dependent study on these materials to be able to understand what is the mechanism of these heat treatments. Again, he does not do everything on his own. There are a lot of other scientists are interested in this, in these studies, and then they come up with this phase where initially it is solid solution strengthening, which transforms to GP zones, which are still coherent interfaces, and then it moves on to theta double prime precipitates. It is still coherent even here, but then this forms into theta prime, which is semi-coherent. then finally it comes down to theta precipitates, which is incoherent, right? It is between, so there is a slight decrease in after the solid solution strengthening, because with increasing alloying element there is copper moving out of the system, so there is a slight decrease, or for the precipitation there is a slight decrease, and then the GP zones form which are coherent but which are precipitates anyway, and then GP zones are formed which are precipitate, the theta prime forms, theta forms. So the maximum hardness is somewhere in between theta prime and theta double prime. We have the max hardness, so we'll have to uh, optimize the heat treatment cycle in such that we are able to get the maximum hardness. We have to optimize the grain size in such that we are able to get the maximum number of precipitates. We have to do a lot of these things. Scientists did a lot of these things to be able to find out a lot what is happening over here. And it is actually because of a lot of these experiments that the steel rigid frame car bodies have moved, and we have a lot of aluminum alloys being used in car bodies, car parts, uh, which have made our cars much more efficient, much more but the engines have become the which is guzzling a lot less oil, environmentally friendly, and we still have a long way to go to find be able. So this is how even an accident inadvertently turns into something very good. Um, we have a lot of such accidental scientific discoveries which have made great news. So this is one of them, and thanks to Alfred Wilm, uh, we are able to achieve a very good. We were able to achieve strength precipitation hardened aluminum alloys. Okay, yeah, it's around 9:05. It's almost time. Um, I'll just wait for a few minutes. I have there is someone in the video call in the lecture right now. If you have any doubts, you can please unmute yourself and we can have a discussion about it. I'll wait for a couple of minutes. If not, we can end the session soon. Okay. Um, I'll end the lecture over here. Um, Thank you so much everyone for joining. We There'll be a few small announcements. The compensatory class for the fifth tutorial will be on April 8th, if I'm not wrong. Just give me a minute. It'll be on the Tuesday. It'll be on the next Tuesday. That is for sure. And next Tuesday is the 8th. So yes, the compensatory class for the fifth tutorial session, which was cancelled because of unfortunate circumstances, unavoidable circumstances, will be on the April 8th, and the final tutorial session for this course will be on the April 11th. Okay, will be next Friday. By next Friday, we'll have completed the entire course. Um, yes, that's it from my side. Thank you so much for joining. Um, See you next week.